The third problem you might face is computation, believe it or not. Do you actually can the supercomputer actually calculate what is needed to be done? It's not hard when there's two goods, food and shelter, and there's 100 people and 50 robots. That's not a very hard problem to solve. We do a lab in this class where we solve something pretty similar to this, okay? It takes a little while, it takes a little work, but a supercomputer could do this really fast. But a realistic economy is much, much bigger, okay? So a realistic economy features millions and millions of products. And for each one of those products, we're going to have to set the marginal rate of technical substitution equal to the marginal rate of technical substitution for everything else, and the marginal rate of substitution incorporating that good for all these consumers equal to everybody else, and compute the production possibilities frontier and do all this. Hey, computers are really good, but they're not infinitely good. And it turns out the size of the problem can break kind of modern computers. Okay, so let's suppose, this is not really something we normally do in this class, but the best algorithms today, well, not the best algorithm, but you can kind of prove that an algorithm is going to require the number of steps to solve an algorithm is proportional to n raised to the power of 3.5. Let me just say, let me write it this way, n to the power of 3.5, where n is the number of products. Okay? Okay, so that means it's not just that you square the number of products, it's not that you take it to the third power, you take it to a little bit higher, and the number, sort of the difficulty of the calculation is going to be proportional to that number. It's not equal to that, there's going to be other stuff in there, but in the long run, that's what it's going to be proportional to. So how big is that problem? Well, a modern desktop, so like a modern computer, at the time I'm writing this, can probably handle a problem with 12 to 13 million variables in not far from a second. Well, maybe a few minutes, but it was a few minutes when we originally calculated this, when I got these slides together a couple of years ago. But for ease of argument, let's say it's in 1 second. Okay, so that means that if you've got an economy with 12 to 13 million different variables, a modern computer system could solve that basically in 1 second. So the question really becomes, how big is n? How many products are there? Is the number of products comparable to 12 to 13 million, or, is it 1,000 times bigger? We could still manage that maybe, or maybe not, right? So in the USSR, in 1983, there were about 12 million different products. So a modern computer could handle that in about a second. No sweat. But it's not really enough to say 12 million different products, because products, if you're going to really think about what a product is across an actual large landscape, it's not just how many, say, coats there are and how many trucks there are. It's also where they are, when needed. So it's not like a coat is a coat. It's like a coat in Moscow is one type of product, and a coat in St. Petersburg is another type of product. And so you have to, and you need them at the right time too, okay? So you have to, if you start to incorporate not just creating the right number of products and having them in some big warehouse, but thinking about transportation and just in time. So it's like you have the right product where it needs to be at the time it needs to be. Well, then you're going to increase the complexity by, say, an order of 1,000. Okay, now you're getting to something like 12 billion different products, and that's in the 1980s in the Soviet Union, where they're using some simplifications. So a problem that's 1,000 times bigger is going to take, 1,000 raised to the power of, where's my pen here? 3.5 more time to solve. And that's 1,000 years at 1 second for a modern computer, okay? So this is telling us that in the 1980s, modern computers would need about 1,000 years to optimally calculate how to allocate all those goods in the Soviet Union and have them be at the right place and right time. But the economy has grown more complicated since, okay? Today, we have 12 million products in Amazon.com alone. And that's not the universe of things. That doesn't include when they're available or where they're available. So the problem has computers have gotten much better too, but the problem of how many things to organize has also gotten just astronomically bigger. And another challenge is that every time you create a new product, so you innovate, that should be a good thing. From the perspective of like the planner who's having to organize this, it's a nightmare because now they have to redo all the things and the problem is going to be harder this time than it was last time. Okay? This was actually like, this computational problem is seen as like actually like a big logistical hurdle for implementing, efficient socialism or efficient central planned economies. And you can read this wonderful book called Red Plenty about life in the Soviet Union in the 1950s and 60s and so on, which is when things were kind of working as well as they ever did. And there's interesting chapters in there about people whose job it is to centrally plan. They didn't have computers that could do this in the time. And so there was people who basically solved these equations and tried to figure out how to allocate resources efficiently. And it was a giant logistical challenge. And of course, you can take shortcuts to make the problem simpler. So have fewer products on offer, kind of have them only be approximately right. So instead of saying it needs to be in like Des Moines, Iowa at this time on this day, just say it needs to be in Iowa on this month. That'll reduce the difficulty of the problem, but at the cost of also making sort of the allocation less than actually optimal, right? From my perspective, like it could be a couple 100 miles away and a couple weeks different from when I need the coat, and that's not that useful to me. Okay, so it's not a problem we're going to focus on in this course. This is more like a computer science type problem, but I just want to point out it is actually a real challenge to figuring out how to centrally organize the thing, and it is a challenge that there are some people who today will argue that computers and algorithms are advanced enough that we can do pretty good, and that this problem has sort of been slain. So that's the controversy.